Hi everyone, and welcome to today's session. Now, I'm really excited because this is going to be the first of a series of lessons on tectonic hazards, so geological hazards. Now, our title for today, I will go through in a minute, but before I do that, what I would like you to do is to put away all your distractions, turn off your phone, I've turned mine off, shut the door, make sure you're not going to be disturbed, and then we're going to have a really, really great lesson. Okay, welcome to today's lesson. So all you are going to need for today is a pen and a piece of paper, and that is literally it. And what I'd like you to do to start is to write down our title. So the title for today is Plate Tectonics Theory. Why do plates move? So write that down, underline it, please. Make sure that you have a question mark at the end because it's a question that you will be able to answer by the end of today's session. Okay, let's get started. So, I think before we even start looking at the theories, it's worth talking about what is the evidence that tectonic plates do move. So, what I'd like you to do is to have a look at the map that is on the screen. Now, this is a map of something that we call Pangea. And Pangea was a theory that a gentleman, a scientist called Alfred Wegener came up with. And he believed that at one point, the Earth's continents looked like this, that they were all squashed together. And that actually over millions and millions of years, because plates move, they've moved apart. And he had some evidence as to why he thought that this had happened. So the first thing, as you can see on this map, is if you have a look at the continent of South America and the continent of Africa, you can see that they almost fit together a little bit like a jigsaw puzzle. And after he'd kind of established that those shapes fitted together, there were also some other discoveries. So they've discovered that actually there are rocks that run down the coast of South America that match the rocks that run down the coast of Africa. And so what they assume from that is that at one time or another, those two continents were actually connected. What's also really interesting is that actually there are similar fossils on both sides of the Atlantic, as in, again, that coast of South America and Africa. And what they concluded from that was that there must be, or must have been at one point, the same animals and the same species that were living in the same place. So those are the three pieces of evidence that plates have actually moved. And as I say, this representation of what the Earth used to look like, that is called Pangea, which is a funny word. So maybe say it after me. Pangea. I'm imagining all of you saying it right now. Pangea. Perfect. Okay. So if there's the evidence for why, the evidence that they have moved, now what we have to have a look at is why. Why do we think that's happened? But there is another piece to the story before we start. Now, if you have a look at this map, that shows us the world's tectonic plates. Now, there are in fact 7 major plates and 8 smaller minor plates. So have a really good look right now. And the major plates are the larger ones. See how many of those you think you can spot. Okay, so I'm hoping that you're saying the Pacific plate, the Antarctic plate, the South American plate, the North American plate, the Eurasian plate. They are the kind of big tectonic plates, African plate as well. Then we have some smaller ones. So as you can see in the middle of the map, there's the Filipino plate, the Cocos plate, the Caribbean plate, the Indian plate, the Arabian plate. These are our kind of littler ones. But all the time, those plates are moving. Now, before we actually study why, we also have to know that there are, in fact, 2 different types of tectonic plate. And they are called oceanic plates and continental plates. And I want you to just have a think. Where do you think oceanic plates are found? And where do you imagine that continental plates are found? Okay, so for those of you that are talking to the screen, which by the way, I encourage, you're absolutely right. Oceanic plates are found underneath oceans, whereas continental plates are found underneath land. So if we were to have a look here at the Pacific plate, and this becomes important kind of in further lessons in the series, you can see that the Pacific plate actually sits underneath the Pacific Ocean. So it's what we call an oceanic plate. Whereas something like the South American plate, that has a big landmass on it. So we would call that one a continental plate. Now, it's definitely worth writing those two things down. So if you need to, pause the video, or if you've already done it, let's carry on. Okay, so what we've got here is a very, very simple diagram of oceanic and continental crust. So our oceanic crust, as you can see, is underneath the ocean, and the continental crust is underneath the land. Now, using the cursor, I'm going to show you this oceanic plate. So just have a look here and follow the cursor with your eyes. You can see that that plate is in fact very narrow. Now, oceanic crust is actually, and I say only, but you'll see why in a second, only 5 to 10 kilometers thick. Whereas when we compare it to the continental crust, which you can see here, again, I'm moving the cursor through it, that is actually 30 to 50 kilometers thick. So our oceanic plate is much thinner than our continental plate. Now, the other thing that's important to know is that our oceanic crust is denser, whereas our continental crust is less dense. Now, part of the reason for that is because the oceanic crust sits underneath all that weight of the ocean. And over time, it's been compressed and compressed and compressed and made smaller and smaller and denser, most importantly. Now, the other thing is oceanic crust is younger and it can be destroyed. So if you have a look here, you can see that the oceanic crust is being forced down underneath the continental crust. And actually what happens is that crust goes back into the mantle and it can be completely destroyed. Whereas we compare it to continental crust is older and it will never be destroyed. Now, in a second, I'm going to ask you to compare these two types of crust, because it's really important that we understand that before we start looking at why plates move, different tectonic plate boundaries, all the exciting things that are to come. So if you want to, pause the video now and just make a note. You might even want to sketch out a little diagram to show your oceanic and your continental crust. Okay, so this is the question that I want to ask you now. Contrast the characteristics of oceanic and continental crust. Now, contrast is another way of saying compare. So compare one thing to another. Now, what I want you to have a think about before you pause the video, before you answer this question, is what words can you use to compare things? Now, I know that you'll do this probably a lot in your English lessons when you're comparing one poem with another. But what language is there that shows you are contrasting or comparing? I mean, it's almost like I can hear your brain working. So I'm thinking that words that might have come up would include however, whereas, in contrast, you could even say that, or in comparison. Now, it's really important when you're answering a contrast question that you use that language, because it shows the person reading it that you are truly saying one thing is like this, whereas the other is like this. So if we start really simply and we think back to the former diagram I showed you, just consider the width of the plates. So for example, our oceanic crust is between 5 and 10 kilometers thick, whereas the continental crust is between 30 and 50 kilometers thick. So I would like you to have a go at answering that question now. I've put some connectives up, even though you've done the thinking already, just in case you need them. So pause the video, and then when you come back, we will go through your answers. Okay, so did you get? Let's go through our answer. So I used my example, the one that I said verbally first. So oceanic plates are between 50 to 10 kilometers thick, whereas continental plates are between 30 to 50 kilometers thick. I've given myself a nice tick there. Then I've got oceanic plates are denser than continental plates. And my last point was oceanic plates can be destroyed, however, continental plates cannot. So I've used all of those connectives. I've compared, or the keyword here is contrasted, 3 different characteristics of oceanic plates with 3 different characteristics of continental plates. So can you now go through the answer that you've got and highlight where you use those connecting words? Because it's a really important skill in geography to be able to do that. Okay. So let's get on to what is actually the crux of the lesson, because now we know about these 2 types of plate, we can actually start to think about why is it that they move. Now, there are in fact 3 theories as to why they moved, but the major theory, which is why we're starting with this one first, is about something called convection currents. Now, what I'd like you to do before I tell you anything about them is actually to just have a really good look at this diagram, because there's a lot of information that's always in diagrams and in the labels that often we tend to ignore, and actually it tells us quite a lot and can be quite helpful in trying to figure it out. So what we've got then, if we start at the bottom of the diagram, we've got the mantle. Now the mantle is that liquid surface, that liquid that sits below the surface of the Earth's crust, which is another one of our labels. What we've also got is this thing, convection currents, and you can see it's in the middle of the yellow circle of arrows. Now, what that shows us is something is happening, something is moving, and then the plates above it are either converging, which means coming together, or they are diverging, which means coming apart. Again, this is going to be super important a bit further down the line. So let's go through what the explanation is of what a convection current is. And then if you want to, pause the video and take down some notes. So, convection currents. The Earth's core is hot and this heats up the mantle. The heated magma rises as it is less dense. As it rises, it cools and it becomes denser again before sinking. So let's relate that to the diagram quickly. So I need to scratch my nose. Let's relate that to the diagram quickly. So we've got the heated magma rising. So that is indicated by the yellow arrows pointing up. And then it becomes less dense. But when it reaches the surface, it gets cooler. So therefore it sinks again because it becomes more dense. This creates what's called a circular movement within the mantle, and they are called convection currents. Now, what happens, and you can see it in this diagram, is the plates sit on top of the mantle, and then the convection currents drag the plates along. So have a read through that again. You don't need to write this down as notes, because what I'm going to ask you to do next will check your understanding. Okay, so what I would like you to do now is to pause the video in just a second. And then I would like you to make a copy of this diagram. And I'm going to ask you to add the following annotations to your diagram. So an annotation it's a bit like a label, but it's a label that offers a full explanation. So if you see what I mean, when you look at the diagram, it says mantle convection currents. It doesn't actually tell you what's going on in each of those places. So what you're going to do is add these annotations that are on the list. The Earth's core is hot and heats the mantle. The heated magma rises. The magma cools and then sinks. And the plates sit on the mantle and are dragged along. Now, what I would like you to do is when you add those annotations, can you please label them 1, 2, 3, and 4? Because whenever you are asked in geography to explain a process, which this is, you always need to do it in the correct order. So pause the video now, take your time with this. I have also done my own version, which you're going to be able to see in just a second, just how dodgy my drawing is. And take your time, get a perfect annotated diagram of convection currents ready. Okay, so I'm vaguely hoping that your diagram looks better than mine because I am definitely no Picasso, but this is my diagram. So I've labeled it at the top convection currents, and then I've added those annotations. Now, what we need to do is, like I told you, start from the first one. So the Earth's core is hot and heats the mantle. Number 2, the heated magma rises. Number 3, the magma cools and sinks. And number 4, the plates sit on the mantle and are dragged along. Now, it's really important when you create a diagram that you add your annotations exactly where that process or that part of the process is happening. So you can see that I've put the Earth's core is hot and heats the mantle at the bottom because that's where the mantle is. And then I've labeled that upward arrow saying the magma rises, so on, so on. So give yourself a big tick for each of the annotations that you got correct. If there's anything that you need to steal from my diagram, please do. I don't mind at all. And then let's crack on. Okay, so at the start of this session, I told you there were 3 theories about why it is that tectonic plates move. These are the other 2 theories. So we have convection currents as our number 1 theory. But there is also theory 2, which is about ridge push, and theory 3, which is about slab pull. Now, theory 2, ridge push, essentially argues that mid-ocean ridges are higher than the rest of the ocean floor. So gravity is causing the ridge to force the plate down. Now, when we start to have a look at tectonic plate boundaries, this will become more important. But for now, you just need to make a note of it. So pause the video if you want to now, or wait for me to finish explaining slab pull, and then off you go. Okay, so slab pull is theory 3. Now, this seems like a fairly obvious statement, but tectonic plates are heavy, really, really heavy. So when a plate has started to subduct, sink, gravity and the fact that it is denser means that they pull the rest of the plate down with it. Now, there are 2 key words in here that we really need to focus on. And the first one is that word that I've highlighted, which is subduct. Now, subduct is a really important geographical term when we're talking about tectonics. When one plate is forced under the other, it begins to sink, and that process is subduction, or to subduct. And actually, the second word that's important is the one about it being denser. So it's always our oceanic plate that is subducted below our continental plate. So if you'd like to, pause the video now, take some notes on these 2, and then we're going to start our main task of the session. Okay, so this is the main task of today's lesson. And what I'm asking you to do is, using the diagram, explain why tectonic plates move. And that question is going to be worth 4 marks. Now, this is a really, really common exam question. And often you will get given a diagram and you need to make reference to it to make sure that you get the marks. Now, the question here is explain. So that means we have to give reasons why the tectonic plate moves. But we need to use the diagram. So let's take a look at it before you guys start. Now, what you can see is actually you've got 2 plates moving apart from each other. They are what we call diverging. But you can see that you've got the yellow arrows in the middle that indicate that heat is being transferred up through the mantle. So this diagram is actually referring to convection currents. So what I would like you to do is, using the theory of convection currents, I want you to explain why tectonic plates move. But I've got some sentence starters. They're probably not even what you class as sentence starters, but they're what you do to show that you are doing things in the correct order. So firstly, this happens. Then this happens. This then leads to, or this means that, and then finally. Now, if you use those, you are essentially time stamping your answer. And that means you're going to be getting it in the correct order. So pause the video now, use the diagram that you created earlier in the session to help you if you need to. And then when you're ready, come back and we will go through the answers. Okay, So let's go through our answers and check that we got everything correct. Now, in this answer, because it was an exam style question, instead of giving you nice ticks, what I have done is given a little 1 in brackets, and that symbolizes, there's the word, where you would have got a mark. So the Earth's core is hot and heats the mantle. And then look, there's my first of those timestamps. Firstly, the heated magma rises as it is less dense. Then, as it rises, it cools, which makes it denser again, and so it sinks. This creates a circular movement within the mantle called convection currents. Finally, the plates sitting on top of the mantle are dragged along by the convection currents. So nice and simple. I literally used my diagram that I created, but I made sure that I use those timestamps because then it shows that I understand the order in which a process takes place. Right, go through your answer. You don't have to give yourself a 1. You can give yourself a big tick for each of the points that you made. Can you again highlight where you use the word firstly, then this, finally, so that you've got it really clear? And then that is the end of today's session.